E658, lecture 22. So in the last class, we figured out one way of, a hardware efficient way of making a circuit which will take two voltages and figure out which one is greater. And the motivation behind trying to build such a circuit was that once we build this and somehow incorporate a reference in the other, incorporate an offset. In other words, we so far figured out, if we figure out how to find if V1 is greater than, if Vin is greater than 0 or not, then hopefully by some reasonably straightforward trick you'll be able to figure out if Vin is greater than some Vref, not necessarily 0. Alright? Once you figure that out, you put many of these guys together. Okay? Some of them are operating, each one of them is operating on a different reference. And then you put many of these guys together and each of the, based on the logical outputs of each of these guys, you should be able to figure out where the input lies. Okay? That's the flash AD converter. So yesterday, we stopped this at this point where we recognize the fact that to minimize the regenerative time constant, what you need is to have as small a capacitance on these nodes as possible, right? And we said that these have to be charged during a phase phi 1. So this is VCM plus, what do we call this? Delta V. And this is VCM minus delta V. Alright. So during phase phi 1, the parasitic capacitances, the left and right nodes are connected to the input sources. Okay. And the parasitic capacitances at these nodes, which are basically, there will be one parasitic here, okay, which I called, I think, CP2, and one parasitic here, which I called CP1. CP1 represents the input parasitic capacitance of the CMOS inverter, right? That consists of two gate capacitances, the gate capacitance of the NMOS transistor and the gate capacitance of the PMOS transistor, alright? CP2 represents the output parasitic of the inverter. That represents the depletion region capacitances from between the drain and the bulk for both the NMOS and the PMOS transistors. And in general, the two will not be equal, so that's why I denoted them by CP1 and CP2. On the other node, it's the opposite thing that happens. So you have CP1 here and CP2, assuming both the inverters are identical. Alright? In either case, the total parasitic capacitance on both nodes is CP1 plus CP2. So the regenerative time constant is the lowest it can possibly be if you mandate that you've done a reasonably good job with the CMOS inverters. Alright? So during phi 1, the two inputs are jammed to VCM plus delta V and VCM minus delta V. So what, and then when I open the switch, these inverters will do their thing and then the whole thing will regenerate. Alright? So can anybody think of what problem there is with this circuit? If there's no problem, we move on with life, right? If there's a problem, we just figure out what the problem is and fix it. What is the problem? See, if you take a CMOS inverter and if the input is VDD, the output is ground, what is the quiescent current drawn by the inverter? 0. So power drawn is 0 because the PMOS is on, the NMOS transistor is on and the PMOS transistor is off, so there is no path for current to flow. Alright? When the input is 0 and the output is VDD, the power is drawn again is 0. Right? So there is no static power being drawn by the CMOS transistor. Now what happens when this is mid-rail, like say some VCM, somewhere between 0 and VDD, let's say this is VDD by 2, what do you think happens? Both the transistors are on, so there will be a huge current being drawn from the power supply and getting pushed into ground. So this draws a lot of static power. So the issue with this scheme as such is static power dissipation of the CMOS inverters. Alright, please note that during phi 1, we don't require the inverters to regenerate. We are just trying to charge the parasitic capacitances at the left and right nodes to the appropriate values. Alright? But if we just did this, which at first sight seems like a reasonable thing to do, you quickly see that while it is true that the two voltages will be charged to whatever you want, the inverters draw a huge amount of power. Does that make sense? Okay, so now that you know, so what do you want to do? So what is the fix to the problem? Okay, one solution is, okay, you turn on the switches phi 1 for a very small time, right? Okay, so anybody wants to discuss any issues with that solution? So if you turn on the switch for a very short time, what are you doing? Finally the input, those capacitances will charge from the input through the resistance of the switch, right? So if you turn it on for an infinitesimally small time, the RC time constant of that RC network, will limit these capacitors will not get charged to there. That's one problem, okay? Alright, but is there something else that you can do? Great. So the problem is that during phi 1, when phi 1 is on, the inverters were drawing current. So if you tri-state the inverters during that phase, in other words, the inverter is drawing current from the supply and putting it to ground. So if you disable the inverters, if you make the inverters dead during phi 1, then you will not be drawing power in phi 1. Okay, and when you want to open these switches, these input switches at the end of phi 1, and when you want to regenerate, you can then turn on the inverters. Does that make sense? Okay, so if I tri-state the inverters in phase phi 1. Okay, so if I now get down to circuits. Okay, I will draw the schematic of the inverters. So what should I do? So these are the two inverters back to back. If you notice on this side, all that you have is two inverters back to back, right? Which is the same as this chap here. This is one inverter, this is another inverter. The output of one inverter is connected to the input of the other and vice versa. Alright? Now, you need to insert, of course we need to add the input switches. So let's, so this is VCM plus delta V. This is VCM minus delta V. Alright? So during phi 1, this is VDD, this is ground. Alright? So when phi 1 is high, what should those switches be doing? Off. So they should be controlled by phi 1 bar. So the question is, do you need switches in both places? Right. So if the question is, do we need both switches? And the answer is yes, we do, because if only one switch was on, let's say we didn't have this switch, so this is always shorted to ground. Then what happens? When you connect them to the input, it will not draw current through this path, right? But it will draw current from the input side, right? So you definitely need both switches. Is that clear? Alright. So needless to say, this is a very popular latch, okay, and we've used it many times in our own designs, and I've seen it in a lot of other designs too. And so during phi 1, what is the input impedance differentially looking in? so as far as the input differential source is concerned, which is trying to charge up these parasitic capacitances, okay, the input impedance looks pretty much like an open circuit except for these small parasitic capacitances. Okay, please note that the sources of these transistors are all floating, right? Okay, so the gate source capacitance of the MOSFET is also greatly reduced, okay, because the source is floating. All right. So the input impedance is simply the parasitic capacitance at nodes X and Y, where this is X, this is Y. All right. And when phi 1 is opened, phi 1 bar closes. So the inverter will simply regenerate. What happens? Whatever difference there is between X and Y, it will simply regenerate in the sense that if X was higher than Y, it will tend to go even higher, right? And eventually, because of positive feedback, the node voltage X will go to VDD and node voltage Y will go to ground. Does it make sense? Okay. So to draw the waveforms, okay, again another minor point that I wish to add is that in practice, though you say phi 1 and phi 1 bar, okay, they will not be exactly complementary, isn't it? So when you generate, how will you generate phi 1 bar? You probably take phi 1 and pass it to an inverter. And if you look at the two, they will be overlapping for a small amount of time equal to the inverter delay. Okay. So a safe strategy to prevent this from happening is to use a non-overlapping clock phi. So if I draw the waveforms, let's say this is phi 1, this is phi 2, okay, right. So if I denote the input by let me say this was one input, this is the other input. So one of these guys is VCM plus delta V. Obviously delta V is a function of time. This is VCM minus delta V, which is also a function of time. It's a fully differential input. Okay. So the average value of both these guys is VCM. All right. Now, what can you say about the node potential at the potential at node X? During phi 1, it will follow VCM plus delta V, alright. Then there is a non-overlap period between phi 1 and phi 2. So what do you expect to happen in that non-overlapping period if all the switches are ideal? It will simply remain held until phi 2 comes along. Okay. What happens to the voltage at node Y? It will follow VCM minus delta V until the falling edge of phi 1. Then it will continue to get held until phi 2 comes along. Okay. Then what happens? So this regeneration begins. So what happens is this goes to VDD, this goes to ground. Alright? And then what happens? Again there is a non-overlapping period, remains held. Okay? And then what happens? it simply follows alright. Oops, sorry. Yeah. It's supposed to follow the bottom one, that is correct. Okay. Alright. And then again it remains held. Alright. And then regenerates. And so on. Does it make sense? Alright. Okay. Now, clearly, what is the sampling instant of the, if the input is a continuous time signal as in this one, the sampling instant is what? What is the difference voltage which is being regenerated? The input is continuous time, so the difference is varying all the time. But the output corresponds to an input looked at what time? What is the value being regenerated? It is this value. This is when regeneration begins. And this value is the same as this value. Correct? So, what is the input which is being regenerated? Falling edge of phi 1. Now, the next thing I wish to add is the following, which is, what about the outputs? When are the outputs logically valid? The outputs are valid a little after rising edge of phi 2. You understand why is the output, I mean, so when do you think the outputs are logically valid? They're definitely valid at the falling edge of phi 2, but when is the earliest I can grab the output? So I just need to wait for a little time to allow for regeneration, right? So once the difference is regenerated to a sufficiently large level, then the outputs, each of them will not be will no longer be in no man's land, okay, for the digital designer. So once I wait for a sufficiently long time, okay, I can simply grab the output. So this is the regeneration window, right? Once regeneration is complete, I should be able to simply grab I should be able to grab my data as, in principle, as soon as my regeneration is complete, to some reasonable extent, okay? We'll get into the details of what this extent is and all that a little down the line, but this is the basic idea. And so you should hold on to the data, the regenerated output, when? Well, finally you want digital output, right? So the output waveforms of this latch are, for some time they're all analog, for some time they are digital logical levels. So you need to hold on to this, grab this data and hold on to it. Presumably you want the output to be held for a full clock cycle, right? In all digital systems, you want the outputs, the logic levels, to be held for a full clock cycle. So I can't just go take this and give it to somebody. They'll get horribly confused because during some time, some parts of the cycle, the output voltages do not make any sense as far as a digital designer is concerned. Does that make sense? So what should I do? I need to simply sample the output at during phi 2, preferably, I mean, as close to the edge of, as just before phi 2 is falling down, I should simply sample it, okay, and hold on to it, right? And that's quite straightforward. You can use a latch, a flip-flop to simply do that. Okay? Does it make sense? Alright. So let's see what all problems there exist with this chap. I mean, as I discussed yesterday, there is no problem when the difference between the inputs is large. I mean, even visually you can look at it, and I mean, if things are so good that you can look at it visually and figure out which is higher, okay, it's most likely that a circuit will be able to do a much better job of it, right? The problem comes, when does the problem come? The problem comes only when the difference between the two inputs is very, very, very small. So let's see what happens in that case. Okay, I will take a case where I don't know, manipulate my data such that it is okay. So during phi 1, let's say it was like this. Then okay, this is my positive input. This is my negative input. And by the way, they should be symmetric. Okay. So these are my two inputs. I mean, finally, you're supposed to be able to digitize any input, right? So these are two conceivable inputs. This is VCM plus, VCM minus delta V of t, and this is VCM plus delta V. Okay. As usual, in this period, there is no change in the waveforms. Okay. So during phi 1, the two nodes X and Y track the input. Okay. Then there is the non-overlap period. The voltages on those capacitors remain the same. Then they regenerate. Alright. Now what happens? The real action starts here now. Okay. What happens to phi 2? I mean, now when phi 1 goes high again, what happens? Both the waveforms, the node potentials at X and Y will attempt to track the inputs, okay? And we see that so this is the so-called sampling instant. What do you think happens? Okay, so if the resistance of the switch is high, I mean, finally please note that the nodes X and Y are being charged from the inputs through the switch resistance, right? So the time constant involved in that charging and discharging is R of the switch times C parasitic, okay? So in all these diagrams, the clock periods are all vastly exaggerated. As I kept telling you yesterday, a flash converter is used when you need to do this very, very, very quickly. So the clock, the time available will be very, very short when compared to the time constants of, they'll all be of the order of few time constants of the RC charging switch resistance times parasitic capacitance. Okay. The only reason I've shown everything dilated here is, to be able to draw diagrams with reasonable ease. So, ideally, if the switch resistance was 0, then this should have come down right away, and you do this, and this should have come up like this, and then it does this, and at the falling edge of phi 1, the node Y is greater than that of X. So what would you expect? You would expect the outputs to do this. Does that make sense? Okay. Now, what do you think happens now? If the switch has got finite resistance, what do you think will happen? See, okay, let's think about it this way, right? So you have, you see the problem, it's VCM, one of the inputs is VCM plus delta V, alright? there is some resistance R of the switch. This is another R of the switch. This is VCM minus delta V. Okay. This capacitance was charged to, both of these are parasitic capacitances which I will call CP. This capacitance was charged to just before, just before the rising edge of phi 1 here. What are the charges on the capacitors? One is charged to VDD, the other is charged to ground. Okay? And what are you interested in? You are interested in the difference between these two node voltages at the end of phi 1. Okay? So, this is the situation at the beginning of phi 1. Okay? And this is changing as a function of time. Alright? So, if the resistance R of the switch was 0, then what would happen to the capacitor voltages? They'll get immediately charged to VCM plus delta V and VCM minus delta V. Okay? Now, there is a finite resistance of the switch. Okay? And it can also include in R the output impedance of the voltage source that's trying to drive the capacitors. Okay? So, what do you think will happen? So, two things are happening here. You can treat a capacitor with initial conditions, a network of capacitors having initial conditions as voltage sources in series with the capacitances, right? So, you have a linear superposition of what would happen ideally, right? Which is this trying to charge to VCM plus delta V as a function of time, okay? Not only that, this VDD will try to discharge exponentially, correct? So, if the time constant is comparable to the time you have in phi 1, then what do you think will happen? This discharge will be incomplete. Does that make sense? Okay. And when does that hit you hardest? Pardon? When the input difference is very small and it is the opposite of what the decision was in the previous clock instruction. With an ideal switch, it would have just followed the inputs, right? But with a real switch, there is a problem in the sense that this may not have enough time to regenerate, and instead of following the inputs, it's trying to, given enough time, the output will eventually follow the input, right? But in the finite amount of time we have available, that may not be possible. Does that make sense? So, you can see that in both these waveforms are exponentially trying to approach these guys. Okay? So, this character is trying to approach which waveform? The bottom one here, right? Alright? And this guy is trying to approach the top. Okay? And in such situations, you will make an error. So what will happen is that this will do this, get held on here, and the latch simply, during regeneration mode, the latch, the inverters don't know anything, they just think this is the right thing to do, and they will do this. Okay? So this is a error in the latch out. Please note that this error doesn't hit you every time. It only hits you when in the nth clock cycle the output was something, and in the next clock cycle the input happens to be of the opposite sign and very, very, very small. Okay? So, pardon?
It can be even negatively large and still we will have
no. If the Okay, the question is why should the input be of the opposite sign? Of the opposite sign we all understand, but why should it be small? What happens if it is large and negative? So if this was large and negative, what would happen? The waveform would tend to do this, even though it doesn't completely charge. As long as it crosses the threshold, you're fine. Okay? It doesn't have to go and touch those waveforms properly. You're only interested in the sign. Does make sense? Okay? So the critical thing is when you have a small input of the opposite sign that you had in the previous clock cycle. Okay? And this is always the best, the most stressful signal for a comparator, because this is when you're most likely to make an error. And we'll figure out how to fix this problem, but in principle, this is what happens. Okay? So this is called hysteresis. Right? What is hysteria? Hysteria is, originally dates back to, the original Greek thing is, it means remembering the past. Okay? So you can see that this is happening because the latch is not being cleared of its past history. Okay? It remembers that last time, this was, the outputs were PDD and 0, and it is still not completely forgotten those two. It's trying to forget, okay, the bad past, and trying to move on, right? But there is still, it only can go exponentially down. Okay? You understand? So now you know the problem. So you should be able to tell me what the solution is. How will you fix this as engineers? As somebody points out, what you need to do, what you could do is the following. It is, so if you start off, if you start off the beginning of phi 1 with the same state regardless of previous history, if you somehow clear the history of the parasitic on the the previous decisions on those parasitic capacitances Cp, then you don't remember the past, right? So hopefully you're doing a lot better. And in looking at this diagram conceptually, can you tell me the simplest thing to do? Short? One thing we could do is short the capacitor to ground, but what is the better way of doing? Short it to what voltage is the better thing? Well, the simple thing is to simply short both these capacitors together. Alright, you could short each of them individually to VCM, okay, which is about VDD by 2. Alright, but you can avoid having to having two switches by simply having one switch and shorting the two nodes together. Naturally, the two capacitors will come to, the voltages will become the same. Okay, if they're given enough time. All right. So one argument that you could make is, hey, if this switch has a problem, discharging this capacitance, okay, so will this switch. Isn't it? So how are you doing any better now than you were doing before? Is that clear? Okay. So the answer to that is that in practice, this resistance is not just simply that of the switch at the input. It also is the output impedance of the amplifier that is driving the latch. Okay. So this R will be typically much larger than just the resistance of the switch itself. Okay. So by adding a switch here, alright, you can clear the memory of the latch regarding the past decision, and you turn over a new leaf every clock cycle. Does that make sense? So if you are to implement this, okay, all that I need to do is add a switch here. Okay, I'll call that RST, stands for reset. Okay, Now you have to figure out the timing. So if this is phi 1, this should be phi 2, alright. Okay. So when should the latch be reset? So after you grab the data from the latch, okay, make sure that you don't need it anymore, because the moment you reset, you lost all memory, right? You don't know what the previous decision was. So after phi 2 and before phi 1 goes up again, this is when you must have reset. Okay, so let me call that RST. So during phi 1, you charge the two parasitic during phi 1 you disable the inverters, okay. You charge the two parasitic capacitances to the differential input voltage, then you let the thing regenerate, right. Towards the end of regeneration, you make sure that you grab the digital data that's on the two nodes, okay, X and Y, alright. Then what happens? Then you reset both the nodes. So both the nodes will come down to VDD by 2, alright, and then you start life afresh. So the voltages, so if I had to redraw this diagram, what will happen? The reset phase is here. Okay. Alright. So what will happen to the output nodes now? What will happen? During the reset phase, both the output voltages will drop to VDD by 2, okay, and then they will start. One will go track VCM plus Vref, the other one will track VCM minus Vref, okay. And as you can see, it will regenerate and then again come back to VDD by 2 and so on. Okay? Does it make sense? Alright? So in a practical design, as I said, the waveforms at nodes X and Y will look crazy.